Hello, Professor Lawman. This is my project. Take a good look at it before I go through and explain it. Here we go. So, start with step one. We start with this launcher. There's a rubber band, so when you pull it back, you store elastic energy. You create elastic potential energy when you pull this back. You pull the car back with it, and then you let go, and it creates a linear motion. One thing to note is that since it's a linear motion, you can use the kinematic equations to solve for velocity, acceleration, position, or time. Then we go to step two, the circular motion. This is the circular track. The car will go around it. We know that acceleration of circular, the radial acceleration will be inwards towards the center, and the acceleration will be equal to the velocity squared over the radius. So after the car goes into a loop-to-loop, it's going to ram into this ball. This bouncy ball is going to be projectile motion because it will be flung off this ledge right here, and the X and Y position will change as the ball goes down towards the dominoes. It's going to create a parabolic curve going downwards, and the parabolic curve is at its maximum height, and at theta equals 0 when it's at the very top of the ledge. Okay, that's step 3. Now we go into step 4. Go to the dominoes. Dominoes are vibrational motion. They will fall one after another, creating this vibrational motion. Kinetic energy. I'll mention some energy transfers right now. You have the potential energy into kinetic energy over here, and then kinetic energy to kinetic energy. But now we're gonna have the ball is going to transfer kinetic energy here, and it's going to be used one after another to knock into the tower, and that tower has stored potential energy. As you can see, there's a triggering mechanism here that we've made with the tower. There's a string attached to 2 paper clips. One is holding back a marble, the other is on top of the tower. Whenever the tower falls, the potential energy mgh from the paper clip will cause it to fall, turning it into kinetic energy. There'll be a tension in the rope, and the tension force will pull down on the other paper clip, releasing the marble. Now we've made use of some special objects here. We've made use of ramps. The ball will fall from one ramp and will fall to the next ramp, and then it will go through the box. There's a hole in the box, as you can see, and it will go through there, down this one last ramp. It'll go all the way through here, and then we get to the next step. This is dominoes number 2, and again it's just a vibrational motion. And then we get to another tower, tower number 2, which is going to do the similar thing. It's attached to a string, and there's a weight attached at the top of the tower. When the tower goes down, its potential energy will turn into kinetic energy, and it will fall, causing this jack to release this pencil pendulum. As you can see here, it's going to rotate about this its radius. It's another circular motion, as we talked about, and its acceleration is going to be equal to v squared over r. And we're going to have it swing. It's going to trigger. The jack is going to fall to the floor. The pencil will trigger, and it will hit this mechanism that we have right here. So let me break this down for you. It's a propeller tied around by a pencil, and there's a weight at the top of the pencil. So this is going to be rotational motion, because it rotates about a single point in the center. And so we have this pencil propped up by this cardboard. So it's going to have potential energy at the top with that weight on top of it. The weight is attached to a string, which will pull a mouse trap and trigger that as well. So let's just talk about some of the physical properties that we have here. So we can see that the potential energy is going to be stored up there, but it will soon transfer into kinetic energy as it falls. When the pencil hits it, it's going to trigger the pencil to rotate about an axis. This kinetic energy is going to be equal to 1/2 times the inertia times the angular velocity squared. It will fall, it'll trigger that, and we'll get to our next step. We get to the mousetrap. The mousetrap is also rotational motion as it rotates about a point. It has a little sharpened end attached to the end of the mousetrap, which whenever it flings about its ass, rotates about the axis, it will again turn that potential energy into kinetic energy, and there will be a change in into transfer of energies right here. And again, since it's rotational motion, the kinetic energy is going to be equal to 1/2 times the inertia times the angular velocity squared. So here we have this is where the water balloon will go, and it will fall right in here, and then the mousetrap will trigger the water balloon to pop, and then the water will flow through these tubes, and finally it will fall and knock over the soap. Some interesting physics that we've learned about water fluid motion is like we can tell the pressure in the water balloon by Bernoulli's equation, and we can tell that Bernoulli's equation is pressure times rho GH plus rho GH, and we can calculate the pressure. Also, some unique physical property that we can attribute to these tubes, because there's a much bigger tube in here, and it leads out into another smaller tube. We can use the formula A1 area times velocity equals the new area and the new velocity. So there's going to be, since there's a bigger tube within here, there's going to be a less area in this smaller tube, so that will cause the velocity to increase and the water will shoot out faster. And here it will knock into the soap. The soap is going to be a regular linear motion. It's after it rotates about and falls to where it's gravitational to its center of mass, and it will fall linearly and land in the sink. So that's what we have for you. Now we'll show you a video demonstration of the video, what we captured from our trials, and we'll show you the best of what we got. Thank you. Test 1, 3, 2, 1.
Ah, shoot.
Okay, we're gonna trigger this. Trigger this one as well. We'll trigger this one as well. It didn't come off. So Professor Lohman, that concludes our Rube Goldberg experiment. We had 13 steps in all, and we had to do 3 manual interventions in order for the project to work to completion, but there's our project. I hope you enjoyed it. Have a blessed day, and have a nice day. Bye.